great personal pleasure that I introduce the colloquium speaker this afternoon, Peter Michelson, who to most people here needs no introduction, but I will give it anyway. Peter has been a colleague for 25 years or more, and he got his bachelor's, I think, in Santa Clara, and then has been at Stanford more or less ever since, including the sabbatical, which he is now on, and has not left town for. So Peter had worked in experimental physics. One of his earlier projects was building a bar detector for gravitational radiation, and he made the first detection of gravitational radiation, gravitational waves. Unfortunately, it was the Loma Prieta earthquake, and so he then moved on to get involved in gamma ray astronomy and worked on the egret experiment, and he was co-PI, I think, on that. And that was wonderfully successful and opened the window on the universe at gamma rays, high-energy gamma rays, and then from there, for over a 10-year period, was put together the Fermi Gamma Ray Space Telescope, building a major project, and in particular being the PI, of the major instrument on it, the Large Area Telescope. And this has been a wonderful 15-year adventure for all of us who've been involved with this project, including Vahe here. And he's going to tell us about, I think, a little bit about how projects actually work, but also about the science, the huge amount of largely unexpected science. And this is, I think, I hope a message that Peter's going to give is how much discovery there is from big projects, especially when you're opening up a new window on the universe. So, Peter, thank you very much for all you've done in leading this project, and as a very happy customer of your leadership under that. And now tell us about Fermi in its troublesome teams. Thank you.
Okay, Roger, I remember thank you. The Loma Prieta earthquake, there was a physics colloquium that day, and at 5 p.m., I don't remember who the host was, but I don't even remember who the speaker was. But at 5 p.m., the floor was open for questions, and then the room started shaking, and everybody ran out. And it was a rather scary day. But anyway, after that, I decided I've had enough of gravity waves for now, particularly that kind. Anyway, I'll actually come back to gravitational radiation during this talk, because there is a connection between Fermi and gravitational radiation. So I'm pleased to really talk about 15 years of observation, almost 15 years of observations with Fermi. It was launched into orbit on June 11th, 2008. So this summer will be the 15th anniversary of that. And I think to set some context, and Roger alluded to this, that, if you think about observing the universe we all live in, that the visible spectrum, which for centuries was our window, is really only a very small fraction of what's now available, the more than 25 orders of magnitude of the electromagnetic spectrum through which we gather information about the universe. And that's not even mentioning, but we'll get to it, other windows that are opening, including particularly gravitational waves, neutrinos, and perhaps other exotic particles that are eventually going to be found, hopefully. Okay, so that picture, I love this. This was from NASA. That strip you see across there is a collage of optical images of the plane of the Milky Way galaxy, and now we have all of this part of the electromagnetic spectrum of that available to study what's going on. But this kind of ignores one aspect that I think gamma ray astronomy and other wavelength bands, but gamma rays in particular, should not be forgotten about, and it's that there are many transient time-dependent phenomena. So the sky is flickering like crazy in gamma rays. And And that's an important aspect of the exploration that we've done with Fermi. So there are two instruments on Fermi that Roger mentioned. The gamma ray burst monitor, or GBM as it's known, is designed to detect gamma ray bursts from hard X-rays, 8 kilovolts up to roughly 40 MeV, and is not an imaging instrument, but it does some localization because of the orientation of the different detectors mounted on the spacecraft. And then the Large Area Telescope, which is that box on top, that's what I'm going to talk about. And that covers an energy range. At any one instant of time, the Large Area Telescope can view about 20% of the visible sky. So it has a very large field of view, and that's really important. And for that reason, when the telescope was designed, the spacecraft, unlike its predecessor, which pointed in a particular direction and took many years to cover the entire sky with deep exposures, Fermi covers the entire sky every 90 minutes because it's in fact zenith pointed. Bob?
What's the length scale?
The length scale, that box on the top is 1.8 meters by 1.8 meters. Okay, so don't ask me how long the solar panels are. So that's the telescope, and I'm going to focus on the Large Area Telescope. But before I do, I want to also mention, in putting this collaboration together in this project, it really involved both international and interagency collaboration. In the US, this was supported by NASA and the Department of Energy, and that was a marriage made somewhere. Anyway, but it's worked pretty well. And it also involved agencies in France, Germany, Italy, Japan, and Sweden. And really an incredible collaboration team that really got together and made this thing work. So I'll say a little bit more about that. So what I want to do, in fact, is just lead you through a little bit of background about how this thing works. It is a pair conversion gamma ray telescope, and I'll explain how that works in a moment. And the design and build of the Large Area Telescope really came about because of the formation of an international collaboration that's still working together today. And then finally, I also want to talk about some highlights from 15 years of Fermi observations. I've just selected a few things because I don't want to be, well, I was going to say, I don't want to be Steve Chu and keep you here too long. Oh well, Steve's, oh well. Anyway, and then finally, hopefully, a look ahead to what might be ahead, not only for Fermi, but with the new facilities that are coming online, and starting, I think, next month, the LIGO Virgo Observatory is going to be online again, the Advanced LIGO Observatory. So there's opportunities for gravitational wave detection coincident with transient gamma ray events. So that's the agenda. So pair conversion gamma ray telescopes, how do they work? Well, Fermi works in this energy band from about 20 MeV to 300 GeV. That is the Large Area Telescope. In that energy band, the main way that gamma rays interact, photon interactions with matter, are in fact dominated by pair conversion. And that is the basis for how the telescope works. So you look at that diagram in the lower left, a high energy gamma ray comes in and interacts in some high Z material, a thin film, thin layer of high Z material. In our case, it's tungsten, and there's a stack of these. So there's a reasonable probability that somewhere, as the gamma ray traverses that telescope, it will pair convert. And then immediately after each layer of tungsten, there is a position-sensitive detector, silicon strip detector, and that then detects the passage and the location of the charged particles, the electron-positron pair that came from the pair conversion. And then finally, it all ends up in the, hopefully in that calorimeter at the bottom to measure the energy. Now, the limitations on the angular resolution of this telescope, at low energies, it's set by multiple scattering typically in the conversion layer. So that's why you want very thin layers. And you'd like, ideally, just lots of them and lots of ability to track. But there are power limitations, budget limitations, all kinds of things. So we optimize this with that in mind. And also, at high energies, the angular resolution is limited by the hit precision that comes out of the silicon strip detectors and the lever arm available for the telescope. So that's all part of an optimization. One of the constraints was cost, although that mainly it was power, because we can't just plug this, it can't use a lot of power. I'll come back to that shortly. So in addition, to have decent energy resolution requires a calorimeter of sufficient depth to measure the buildup of an electromagnetic shower in the calorimeter, which is at the bottom there. And then finally, to actually detect gamma rays with high efficiency, one also has to keep in mind that one needs to reject at fairly high level the much larger flux of cosmic rays, charged particles, bombarding the instrument, and the ratio is about 10 to the 4 or 10 to the 5 to 1. And one has to reject those rather efficiently. So that's how a pair conversion telescope broad outline works. Now, a little bit of history. The first, I think, encounter that people at Stanford had with this goes back well before I was here to this gentleman, Robert Hofstadter, who was a member of the physics department for many years. And he's best known for studying the structure of the proton in an accelerator that used to be under what's now the engineering quad. And so Bob did that work, I think in the late 50s or around there. And he got a Nobel Prize for it in 1962. So then later, when I met him when I was a graduate student, I wasn't working with him, but I learned about what he was up to. And I found this picture on the Stanford archive of Bob Hofstadter in his office in 1975, and there's a chalkboard behind him where he sketched out what egret looked like. Now that office no longer has a chalkboard because when Giorgio Grata moved in there, he took the chalkboard down, but anyway.
Whiteboard.
Well, you got a whiteboard, okay. But anyway, Bob had been thinking about this for some time, and this was the design that he and collaborators at the Max Planck Institute in Germany and also at Goddard Space Flight Center, NASA, came up with. So the tracker in this telescope was a externally triggered spark chamber, okay? And so a gamma ray would convert somewhere in the spark chamber, be heading down, the electron-positron pair would head down, they would go through a time-of-flight coincidence system, and then be absorbed in a sodium iodide calorimeter. Now, because they were using a spark chamber, that needs an external trigger. The external trigger was the time-of-flight system, and the absence, to get rid of the charged particle background, the absence of any signal in the anti-coincidence dome. Okay, so that was sort of triggering. And that has some, anyway, that was 1975. This instrument didn't fly until 1991. So, but it flew on the Compton Gamma Ray Observatory. It was one of 4 instruments on the observatory. And at the time it launched, I was actually involved in this project. I had nothing to do with building the instrument, but I learned a lot from this. So, yeah.
So the anti-coincidence dome, the anti-coincidence, is that to shield out all other background?
Yeah, well, if you had like a charged cosmic ray coming in, it would light up. A gamma ray coming in, ideally, wouldn't light it up. But I'll get back to...
You don't have other gamma rays as background?
Yeah, you could have other gamma rays coming in, but the field of view, it requires you have to trigger the time of flight system, and that constrains the field of view. So you're anticipating where I'm going. So anyway, this was the Compton Observatory, and what did we learn from egret, the high energy instrument? I think Roger mentioned this. So by current astronomical standards, this was in fact, at the time, a huge step forward. Looking back, nowadays it doesn't look like a very big step, but at the time it was big. So that, on the left, you see an all-sky map put together from 9 years of observations and above 100 MeV, of complete all-sky survey. And egret discovered, and it was published as the 3rd and final egret catalog 271 gamma ray sources, of which only 171 of them were unidentified. So only about 35% or so, 33%, were actually identified. And most of those were active galaxies and pulsars, but mostly active galaxies in the external to the Milky Way, but a lot of unidentified sources. But nonetheless, the success, these results, and I add this, it's really important, the technical developments in high energy physics, independent of all this, that were taking place in particle accelerator labs, was a strong motivation for developing the Fermi Large Area Telescope. So now I'll turn to how that happened. Try to be brief, but a crucial part of this began with campus SLAC interactions, which were due to the person in the photo on the lower right, Richard Taylor, who had previously been research director at SLAC and actually helped Hofstadter get some beam time at SLAC to actually calibrate egret. So he knew about egret. And at the time, I didn't know Dick Taylor in 1992. And Dick Taylor called me up and said, would I come up to SLAC and give a seminar about egret? So I went up there, and I really didn't know anybody up there. I'd met Taylor. So I went up there, and I gave a seminar about egret, the results from the first year, a little over a year of operation. And during that seminar, that's when the discussion started. And it started with a question from someone in the audience about egret. When I showed that picture of the instrument, namely that, the question was, why did you fly such a dumb design? Okay, that's actually the question I got. And in fact, in the context of where high energy physics was at the time, it was not an unreasonable question, because spark chambers in particular were not used in high energy physics experiments past the late 1960s. And I tried to look into this, but I'm pretty sure that's correct. But somebody knows better, tell me. So the question was, why did you use a spark chamber? And the answer was, well, it takes a long time to space qualify something, and the power consumption has to be very low. Egret used 160 watts of power. Okay, so that's important to keep in mind. But anyway, that was how things got started, and the collaboration built up, first with SLAC, and then with help from Bert Richter and Jonathan Dorfan. I put Steve Chu in there because eventually he went to DOE, but he was department chair here at the time. And we also established a DOE-NASA partnership. And I kind of like this photo on the left, which shows, this is 2004, before launch. There was a review out at Stanford. NASA sent their representative, Paul Hertz, and then also Kathy Turner from DOE. And Kathy and Paul are still with NASA and DOE. So we had this wonderful photo somewhere on San Francisco Bay, and we had a very good partnership between DOE and NASA. So that's where we started. Now it built up, so very quickly, then the instrument. The instrument is shown here. So the tracker, first thing was, it was modular. Egret was very monolithic. A monolithic and a coincidence dome. With Fermi, making it modular and segmented was actually very important. So it consists of a 4x4 array of both tracker and calorimeter modules, and then an anti-coincidence detector that itself is segmented that covers mostly the tracker and the top part of the calorimeter. So you can compare that. So what is the effect of this? Well, the first thing is, compared to egret, the LAT, the Large Area Telescope, has a larger field of view, primarily because there's no time of flight system. So the aspect ratio is much better. Secondly, the improved angular resolution because of the very, very high trigger efficiency and precision of the silicon strip detectors. And finally, the effective area extends well above 10 GeV. By 10 GeV, egret had no effective area. It was very small. And that was because of this backsplash effect. So if you have a high energy gamma ray come in, and it gets the electron-positron pair go into the calorimeter, you develop an electromagnetic shower. And guess what? Some of the particles go back in the direction they were initiated from. And some of them hit the anti-coincidence detector, and that really kills the trigger system for egret. With Fermi LAT, we had a segmented anti-coincidence detector that significantly cut that down. And in addition, we could tailor the trigger so if the energy in the calorimeter were large enough, we just took the event and downloaded it. So our limitation wasn't like egret using up spark chamber gas. It was more just how much telemetry was available. So we could tune that up. So that was a big plus. So what does that mean in terms of performance? I won't go into this in detail, but just for example, you see the effective area there in the upper right for GLAST and egret. And egret pretty much is out of area by about 10 GeV. And the field of view is much larger. So that's the instrument. So now, while we were putting this together, we had been forming an international collaboration. We had participants, collaboration members from France, Italy, Japan, and Sweden. So then NASA decided, okay, because they were the lead, to put out an announcement of opportunity, that is, submit a proposal competitively to build the Large Area Telescope. Okay, and we could use whatever technology we wanted, but we had to propose something that met certain guidelines. So we went through that exercise, and in 1999, we submitted this proposal to NASA, and it's the longest proposal I've ever written. It was about 400 pages long, but they only allowed maybe 100 pages or less for the science part of it, and the rest of it was for the management and the budget. So, but anyway, that's a bit of history. Now, I have to acknowledge, at the time, Artie Bienenstock was the Dean of Research at Stanford, and he really provided a lot of advice and some help in figuring out how to put together a proposal that might actually win. So we did that, we submitted it, and it won, and we were off and running. So now, quickly, I'm just going to show you some hardware real quick. Every one of the subsystems that make up the Large Area Telescope, at least every institution in the collaboration at the time we proposed was involved in at least one or more of the subsystems. And just run through them. The silicon strip detectors, for example, were fabricated in Japan. That part was led by Hiroshima University, had a lot of expertise. And then the INFN, the Italian Nuclear Physics and Particle Physics Institutes in Italy were involved, particularly Trieste. And UC Santa Cruz was the lead in the United States. So that involved a whole lot of assembly work, resulting in a tracker module, or actually 18 of them. 2 of them were flight spares, and we built 16 for flight. And then the cesium iodide calorimeter was also a major effort that involved the Naval Research Lab in the United States, CEA, Saclay in France, as well as IN2P3, Nuclear and Particle Physics Institute in France, and then in Sweden, KTH and Stockholm University. So that was, and they all worked together pretty well most of the time. Okay. Anyway, so that's that. The anti-coincidence detector was led by Goddard Space Flight Center with some technical participation from Fermi Lab that had actually developed ACD tiles with wave-shifting fibers embedded so that one got a uniform response from the anti-coincidence detector. And they developed that. And then finally, SLAC was where ultimately the integration of the instrument, all these subsystems came together at SLAC and were assembled there and tested. And SLAC also had responsibility for a really key part of this thing, which was the data acquisition system. And that was also a big job. Anyway, it all got integrated, and eventually all the pieces came together and went to the US Naval Research Laboratory for thermal vac testing, because to verify it could work in a space environment. So that's the instrument. And then after being tested and signed off on, the instrument was shipped to Gilbert, Arizona, to General Dynamics, who were building the spacecraft. It got integrated there. I'm in that picture somewhere, but I'm not sure who I am. But you can probably recognize all the other people. Anyway, so what you see here is the large area telescope on top. On the sides are various command and control system functions, as well as the gamma ray burst monitor. And then from there it went to Kennedy Space Center. This is spring of 2008. So the spacecraft was being integrated with this thing at the bottom there, which is for interfacing to the rocket. And there it is on top of the rocket on the launch pad with part of the shroud removed. You can see the instrument. So it's ready for launch actually in June of 2008. There it is on the launch pad on top of a Delta II Heavy rocket. Somebody wants to ask me why we use that. You can ask me later. This was June 7th. We had our last opportunity to inspect it. So a group of us were brought there by this group here. I'll just point out the person on the left. I don't know his name, but he was with the United Launch Alliance. They supplied the rocket and all that. Next to him is Neil Garrels, who unfortunately passed away a few years ago. He was a very valued collaborator at Goddard and on Fermi for many years. And the Swift telescope, in fact, now is named after him. He was the PI on that. And then David Thompson, and in the middle there is Julie McHenry, who at the time was the deputy project scientist at Goddard and also a collaboration member. She, shortly after this, became the project scientist for the mission. And then that's me, and then that's another person from the United Launch Alliance, and then Bill Atwood, so from SLAC and then UC Santa Cruz. So we were ready to launch, and it was launched. Okay, now that's not actually how it was launched, but anyway. Somebody at the United Launch Alliance actually set this up and said, here, take a picture, that they put a cord in there, and anyway, it was kind of nice, but that's not how it was launched. But anyway, it took off at 12:05 p.m. Eastern Standard Time, and I can say we weren't this close to the launch. We were on a beach nearby looking at it, and all I can think when that thing was going up was, let's see, we worked on this thing from 1992 when we first had the idea to 2008, and now it all depends on that rocket not blowing up. Anyway, it didn't blow up. So it made it to orbit, and now before it was launched, it was known as GLAST, Gamma Ray Large Area Space Telescope. Okay, and NASA decided, with some help, that they typically rename satellites after someone after they're launched and in orbit. So in the case of GLAST, it decided to have they hosted a public competition or nomination process. So people from around the world could submit nominations. And of course, you know the outcome. It was named after Enrico Fermi. But it was, I don't know how close the vote was, or the nominations were, but there were two candidates. One was the Incredible Hulk, I'm not kidding, on the left, and the other was Enrico Fermi. And I don't know if NASA stuffed the ballot box or not, but anyway, Enrico Fermi won. So that was terrific. So we went from there. Now I'll turn to the science. So the 15 years of observations, this collage of different science observational discoveries is part of a poster. You can pick one up here. It was actually done in 2000, sorry, the 10th anniversary, but I've got some copies up here. If you want one, pick one up as you go out of the room. So anyway, 15 years of observations. Now, a key part of this, and I can't emphasize this enough, is the collaboration that built the instrument, developed the analysis tools, all of that. We're also deeply involved in the science and have been ever since. So this is the group we started with. It had 73 members in 5 countries, and it's now grown to 402 members in 25 countries all over the world. And part of the reason for this is that postdocs and grad students who were attending some of the universities in these countries, after they got their PhD or finished a postdoc, wanted to stay involved, but they returned to their home country. And we've always been very open to that participation, so it's largely continued with many. That's one of the main reasons the collaboration has grown like this. And then they start research groups and so forth. So anyway, also I want to just highlight these people. I'm not going to tell you who everyone is here, but members of the collaboration take turns each year being the analysis coordinator to kind of manage the collaboration analysis ongoing activities in 8 or 9 different topical areas. And so every year, someone rotates into that group. And so the first one was Julie McHenry, who I told you about later. Our current analysis coordinator is Melissa Peshka-Rollins, who's at INFN in Pisa, and she's about to step down, and Deirdre Horan, who's at École Polytechnique in France, will come on in March. But I also want to acknowledge a very important contributor who, on an ongoing basis, has really made a lot of this work, and that's Giovanna Senatori, who actually came here with her spouse, who is Nicola Omade, from Pisa for a 1-year visit at Stanford, and they liked it so much they didn't leave. So they're still here. So Giovanna works with the collaboration and manages a lot of the activities of the collaboration. So I want to acknowledge that. All right, the other thing I want to point out, which is also very important, particularly for a mission where you're looking at transient phenomena that come and go, the data is public. Even though the collaboration generates it, but we ship it to Goddard after the pipeline processing at SLAC, and then Goddard has a science support center that makes it all public. And that, during the first year, it wasn't done that way. That was to make sure the instrument was properly calibrated and operating. But after that, it was all public. And that has had I think it's actually important, and I think generally supported by the entire collaboration. So the use of the data, this is from NASA, is really the largest users are in the United States, about a third. Then you see China, Italy, Germany, and a whole bunch of other countries, all partaking in analyzing the data from Fermi. Another thing that has been done, which I think has been extremely successful, is the mission, with the help of the instrument teams, long ago started a series of summer schools for university students from anywhere in the world who would apply and then come typically to a campus in Maryland or Delaware for a summer institute to learn about Fermi data and how to analyze it. And those would typically last about 3 weeks. Those went into hibernation during the pandemic, but they're coming back now. I think that's had also a big impact. Okay, now, back to Fermi, what we actually saw. So this is the egret all-sky map I showed you earlier. 9 years of observations, all summarized in that one image. And with Fermi, it was transformed to that. And if you look carefully, some of those little red dots and things you see off the galactic plane, those are all real sources, and they're active galaxies primarily. So that is the all-sky map from Fermi after 12 years. This is above a few hundred MeV. I've forgotten the energy cut here. If you look at this map, just up front, 70% of the photons in that image are gamma rays that come from diffuse radiation generated in the Milky Way galaxy, from cosmic rays interacting with interstellar radiation fields and interstellar gas. The remainder are from localized sources that are either galactic or extragalactic. And there may be, and I'll get back to this, perhaps there's even an extragalactic, more or less isotropic diffuse radiation. But that's something we wanted to look for. So in terms of catalogs, there's egret, 271 sources, and there's what Fermi, our latest catalog, published last year with over 6,600 sources. A lot more. And in addition, notice that with egret, 67% of that small number were unidentified. With Fermi, that's been, the percentage is cut in half, 32% are unidentified. And that's an ongoing puzzle to figure out what they are. But that's where we are now. The other thing is that egret had identified 3 distinct source classes of high energy gamma ray sources. With Fermi, we now have more than a dozen. So we have to understand them in terms of the physics, how they operate, and the environments in which they evolve. So that's the task. And as I mentioned, The dominant source the dominant source class are extragalactic active galaxies, otherwise known, particular ones known as blazars, that basically have, and the world's experts sitting right up here, but these blazars basically are active galactic nuclei with relativistic jets that are oriented close to the line of sight to Earth, and they are powered by accretion and rotational energy extraction from a massive, supermassive black hole. So that's sort of the big picture of those, and there are various cartoon versions of this. And the thing about this kind of source, number one, you cannot treat a gamma ray source as a spherical cow. Okay, you have to, the orientation is crucial. And with Fermi, we get a sample of lots of sources from different angles, and active galaxies are one example. So that's important. Now, there have been many others on many different length scales. From very close by, we've seen terrestrial gamma ray flashes generated in the Earth's atmosphere. Many of those. Solar flares, and a variety of other things. So I'll just talk about a few of these in the time remaining. Okay, so first, there's a very famous, well, back in 2010, 2 years into the mission, a group at Harvard, led by Doug Finkbeiner, with publicly available Fermi data, did some analysis following up on some work they'd done looking at something called the WMAP haze from the Wilson microwave anisotropy probe, and also some evidence in ROSAT that there were, well, they inferred that there were two large gamma ray bubbles that were extending about 50 degrees above and below the galactic plane and about 40 degrees wide. So this is a somewhat enhanced version where the galactic foreground, a model of it has been subtracted, and they didn't include the galactic plane. But this is published in 2010 by Doug Finkbeiner, Tracy Slater, who's now at MIT, and Ming Su, who I think is now University of Hong Kong. So if one looks at the scale of this, assuming it's at the galactic center distance scale, 50 degrees is about 30,000 light years. So the question is, what are these? How did they come about? And this shows a little bit of results published by Planck in 2013, where they detected a galactic haze that in some ways is consistent with the morphology of the Fermi bubbles. But I think there's still a lot more work to do to figure out what these actually are. But at least two alternative energy sources have been proposed for these bubbles, okay? One is that the central supermassive black hole plays a role, Sagittarius A star. The other is that perhaps there's a lot of star formation near the galactic center, and both can supply the energy overall, but in fact on different timescales. So I'm going to cut through the rest of this pretty quickly, but part of the puzzle to fill it all in, you need multi-wavelength observations. So that's been done in X-rays, most recently with E. Rosita, and they published something in Nature in 2021. And then there have also been spectroscopic studies, UV absorption line measurements, and H1 kinematic studies of clouds within these Fermi bubbles, and that's revealed some interesting things. So a lot more work to do to understand these. Anyway, another question, which I mentioned earlier. You look at this and you say, is there in fact any evidence of an isotropic, diffuse, perhaps primordial, extragalactic gamma ray background? And the simple answer is probably not. But that was an investigation that was led by Marco Aiello and some of our collaborators, who Marco was a postdoc at SLAC and then went to Clemson University. So they did an analysis of looking above 50 GeV. So the first thing was a catalog of sources above 50 GeV, very high energies, where the angular resolution is really quite good. And that was published in 2016, and then following up on that in 2016 also, there was a study done, and the determination made that at least above 50 GeV, that the point sources would account for at least 72% and up to 100% of the total extragalactic gamma ray background. So it leaves room for unresolved sources or something perhaps more exotic, but it's not a big space available. Okay, so that's interesting. Another thing that was done, going a little bit lower in energy to 10 GeV, there's another way that these high energy blazars, which are the dominant source in the sky, 2/3 of the 6,600 sources that we published last year are blazars. So it turns out if you take a blazar and you move it to higher and higher redshifts, further and further distance, the high energy photons get attenuated because they interact with interstellar radiation. The intergalactic radiation fields, the so-called extragalactic background light. And so only a small fraction, depending on the blazar distance, make it to us at Earth. And over cosmological distance scales, this is in fact best probed by gamma rays in the range 10 to 100 GeV. So this diagram on the left shows you the opacity, and anything above 1 roughly is relatively opaque. And so this was a study that was initiated, also led primarily by Marco Aiello. A lot of work went into this. And the important thing to recognize is that the EBL models, a dominant factor is the star formation rate. And the attenuation measurements, looking at blazars over a broad range of redshifts, suitably calibrated, can distinguish models of star formation history. So that's what they did. And this is the group. I won't go through all this. I'll just skip to, this was published in Science in 2018. This is what they found, that the opacity as a function of redshift is determined by those blue stars. And the gray points on that scale show you for each blazar that was in this sample of 739 blazars, it shows the highest energy photon actually detected from that source over a period of 9 years. Yeah.
You say that this is a graph of opacity, but it's not. It's a graph of energy versus redshift. So what is the opacity?
No, the opacity curve, it's the energy at which the opacity is 1.
Gotcha.
Yeah, okay, sorry. It's not opacity plus. That curve is tau equals 1. Okay, yeah, sorry about that. Okay, so anyway, this was published, as I say, in Science. Now, did we learn anything new from this relative to not using gamma rays, but looking at directly trying to measure the extragalactic background starlight and so forth and model it? And the answer is I don't think so, but I think as it was observed by one of the commentators for Science back when this paper was published, Elisa Prandini, who's a astrophysicist at the University of Padua, she wrote that we found a way to measure star formation, and we found that it peaks at about 3 billion light years after the Big Bang. And although this is similar to previous estimates from optical and infrared observations, the results provide valuable confirmation because they should be affected by very different systematic effects. So I think it's a cross-check on something that's frankly, fairly important to understand. So anyway, that's that. Now, let me now move on back. I haven't talked about the time domain much, so I want to spend the last part of this last 10 minutes talking about discoveries in the time domain. So this is again this map, this chart showing the different sources on different scales from galactic to extragalactic. And I'm going to just talk about a few, but the transient observations, the time-dependent sources that Fermi has detected, span timescales from milliseconds to years, to the entire time we've been in orbit. And that provides different kinds of insights into what's going on. So I'm going to focus on two things, gamma ray bursts and pulsars, okay? So let me start with the gamma ray bursts. And I kind of like this science cover because this was, when was this? 2014. It was a record-setting gamma ray burst that we detected and a bunch of other detectors detected. Got the cover of Science. That's not an actual image. I mean, that's an artist's concept. But we detected gamma ray emission up to 94 GeV with the Large Area Telescope. So anyway, gamma ray bursts, though, have a very long history, which maybe you'd all know about, but just quickly summarize it. They were first discovered in July 2nd, 1967, by the Vela satellites, which were in fact launched by, what was it, the Atomic Energy Commission at the time, as part of monitoring the Nuclear Test Ban Treaty that John F. Kennedy had negotiated. So Kennedy said, put these satellites up. I don't know when they were launched, but they had actually detected explosions coming from outer space. I don't know what they detected looking down at the Earth, but that was the original reason for it. And they didn't publish the result until 1973. But anyway, once that was out, there was a lot of interest in this. And for many years, gamma ray bursts were thought by most to be located in our galaxy. And I think Roger can tell me if I got this wrong, but I think it was mostly because of the energetics.
The spectroscopy.
And the spectroscopy, yeah. But there were a few exceptions to that thinking. What?
There were some wrong
observations, yeah.
Yeah. So anyway, when GRO flew, Compton Gamma Ray Observatory, the burst transient source instrument on that, BATSI, had actually showed there was really a fairly isotropic distribution of bursts on the sky. But it was really in 1997 that an Italian-Dutch X-ray satellite named Beppo-Sachs located a GRB well enough that an associated optical transient was detected and found to be at a redshift of 0.835. So anyway, there was, and the story goes on. Now, I think a very important step forward from Compton Gamma Ray Observatory that's since been very much refined was led by, among others, Krista Cavaliotto, and they published this paper in 1993, fairly early on, of the time duration measured for the gamma ray bursts detected by BATSI, and it was more or less bimodal. And so with a minimum of around 2 seconds, so the short duration bursts were those less than 2 seconds, the long duration bursts longer than 2 seconds. And again, to make a fairly long, complicated story a bit shorter, there were sort of two models put forward, two scenarios for generating gamma ray bursts. The long bursts were thought to be largely associated with this core collapse, this stellar end of life of a massive star, and the formation of a black hole and formation of a jet, a so-called collapsar model. The short duration gamma ray bursts, on the other hand, were thought to could arise from coalescing neutron-star binary or neutron-star black hole binary. Okay, so that's the story, what the thinking was. Now, I'll get to Fermi in a moment. The LAT, since launch, has now detected actually it's a bit more than 210 long duration bursts and only about 10 and 21 short duration bursts. So they outnumber, at least in the LAT, 10 to 1 long versus short. The GBM, which works at much lower energies, much more efficiently detects bursts, and they've detected more than 3,000 gamma ray bursts. So a lot of data. And what have we learned? Well, before I talk a bit more about short duration bursts, there's a process that people were on the lookout for called the R process. It's basically a rapid, by neutron capture, rapid nucleosynthesis of heavy elements, gold, platinum, and so forth. And this likely provides a significant, if not dominant, compared to supernovas, contribution to observed abundance of heavy elements. So these would be observed as what are called kilonova, which would be the radioactive decay of these newly formed and unstable nuclei. And this would power a very rapidly evolving, fairly isotropic emission as a kilonova. And this is sort of, again, a cartoon that kind of illustrates that. So, where did we go? Well, amazing thing happened. I think you all probably know about this. On August 17th, 2017, 2 years after LIGO's detection, or a little year and a half, 2 years, September 2015. Anyway, a little less than 2 years after LIGO detected a black hole binary, they saw this, a coalescence of what was later really determined to be a neutron star binary. And completely independently, the GBM, not the LAT. The LAT did not see this burst, but our sister instrument on Fermi did see it at low energies. There was a short duration burst seen by the GBM about 1.7 seconds later. So there it was, amazing. And the localizations were good enough, and there was enough enthusiasm and interest that more than 70 observatories, both ground and space-based, went after this to do spectroscopy. And I mean, this was just really amazing. And so, really exciting. So what came out of that, among other things, was this really, this paper that, I don't know if it's a record or not. Maybe, do you know? Anyway, I am one of 3,677 authors on this paper, with authors from 35 countries. So every observatory on the planet that either put a limit or added detection observing this system were authors on this paper published in the Astrophysical Journal Letters. And I think it was really a pretty remarkable result. So we hope to see more like this, and I think in the future we will. So that's that. Now, gamma ray burst, to mess the story up a little bit, last year there was this gamma ray burst. The naming of these, by the way, the first part of it, the 21 means 2021. The 1211 is December 11th, and A means there was more than one that day, so they number them A, B, C, D, etc. So this burst was observed and seen in the Large Area Telescope and in the GBM. But it was a long duration burst, about 50 seconds long, at a relatively nearby redshift, 0.07, and it was associated with a kilonova. Now, kilonovas were not supposed to be associated with long duration bursts. They're supposed to be with short duration bursts. So this kind of, you know, it has generated interest. And there have been a number of papers in this issue of Nature in December 2022 about this burst, including the discovery paper, observational electromagnetic optical follow-ups and so forth, and one paper suggesting that, in fact, it could be a neutron star white dwarf merger, a different kind of gamma ray burst. And I think looking forward, if it is a coalescence event, there should be a gravitational wave signal associated with it. So we should be looking at long duration bursts as well as short duration, and just be on the lookout. So I think there's real discovery potential here. Now, not to be outdone, was a burst last year. Every year there's at least one that's like a record setter of some kind. So there was one in October 2022 that someone gave the name BOAT, brightest of all time. So this burst was very, very close, redshift of 0.15, and it was extraordinarily bright, and in fact saturated the anti-coincidence detector on the Large Area Telescope for something like 20 seconds. Just completely saturated it, the X-rays hitting it, and a bunch of other telescopes were saturated as well. But we detected emission up for 10 hours, up to about 100, exceeding 100 GeV, 10 hours. Also, real record setter, a new Cherenkov telescope on a mountaintop in Sichuan province in China, Lhasa, reported detection of more than 5,000 very high energy photon events up to about 18 TeV. Pretty remarkable. So anyway, this is an interesting burst. I'll skip this. Now, last thing, gamma ray pulsars, and then I'll stop. Gamma ray pulsars have been an incredible I think Fermi's contributed a huge amount in this area of science. So gamma ray pulsars were discovered, actually we're going to have a seminar about it, aren't we?
Yeah.
The person who discovered those, the first one is coming here to give the Hofstadter lecture, right? Jocelyn Bell Burnell. That was a radio pulsar. But since then, there have been thousands of pulsars detected, and Fermi has contributed to that, studying the high energy emission. So in the old days, there were 7 gamma ray pulsars known when Fermi launched in 2008 from CGRO days. And the Fermi observations, however, established that there's a large and varied population of these objects. But they are, in fact, the dominant GeV source class in the Milky Way galaxy. And the catalog, which is about to get published, currently has about 294 gamma ray pulsars in it. That exceeds the total of 271 sources seen by Egret. So I think that's a big step forward, but a little bit more on that. So this is, when Fermi launched in 2008, you could summarize everything known about gamma ray pulsars on a postcard. I think Dave Thompson at Goddard did this. It's sometimes called the Thompson postcard. If you look at the other side of the postcard, it tells you where they were. And with Fermi, that's what we now have. So we have a population of gamma ray millisecond pulsars and other younger, longer period pulsars. So a whole lot going on there. How did we find these? Now I should tell you, if you're looking for a gamma ray pulsar, you've got a Fermi source and you say, is it a pulsar? Well, the first thing you might think of is, well, fold the data and see if you can find a spike or Fourier transform or whatever. But remember, the brightest gamma ray pulsar, just to set the stage, is probably the Vela pulsar. Fermi detects about 1 photon, on average, 1 photon every minute or 2 from that pulsar. So you've got a lot of shot noise if you try to do a blind search. But nonetheless, we've done some and found some. But if you want to find millisecond pulsars, it's almost, you got to take a somewhat different approach. So what we did, and this was led by David Smith at Bordeaux and others, they formed a collaboration with a collaboration called the Fermi Pulsar Search Consortium, which involves people who have access and know how to use this wonderful array of large area radio telescopes around the world, all the way from France and India, South Africa, Germany, now the Fast Radio Telescope in China, and one of the oldest telescopes, the Parkes Radio Telescope in Australia. So that group, a group of people associated with those, work with the collaboration to follow up on Fermi sources. And of course, Arecibo, we unfortunately don't have anymore. So one of the first ones, and I just show this because this is the story about the first millisecond pulsar detected by now what is the world's largest single dish radio telescope, 500-meter FAST radio telescope. So FAST looked at a Fermi source and discovered a 5.19 millisecond pulsar there. And it took about 1 hour of observation. They then inform us, this is the period, there's the data. And then we could fold the Fermi data for, at this point, it was about a little over 10 years of data, because we know the period, so we can search for the period derivative in a very constrained way. And we found that it pulses in gamma rays. So that got published shortly after this. Well, it wasn't that short. It was about 2 years later. A paper came out, and there's the paper, the fast discovery of an extremely loud, faint. It was the faintest millisecond pulsar, I think, discovered up till then, at least. And the people involved in that I just want to highlight a few of them. Colin Clark, who's a collaboration member, is at both Jodrell Bank and at the Max Planck Institute for Gravitational Physics. He's been a real leader in all this. Pablo Saz Parkinson had been a student at Stanford, actually at Elliott Bloom at SLAC before Fermi, then went to UC Santa Cruz and has been working in this area. And then Xian Ho, who you see in the upper left, she was a student at the University of Bordeaux in France, worked on Fermi, worked on pulsars in the early days when we were observing, and then she eventually returned to the Yunnan Observatory in China, and she was, played a key role in getting all this going. So and then Dee Lee is an astronomer at I think he was at one point a postdoc at Caltech. And anyway, he's very experienced radio astronomer who really supported this as well. So I think that's a nice result. We're expecting more in the future. The other way, and now I better hurry up, Bruce Allen at the Max Planck Institute also, they were looking for gravity waves, but they had a lot of computing power. They decided to apply some of that to doing blind searches in Fermi data. And so they did something called Einstein at Home, where they did this for gravity waves, but they applied it to the gamma ray data, and there have been about, I forgot how many, about 25% of Fermi pulsars discovered to date have come from blind searches. And this was sort of kicked that off in a very nice way. And it involves the public. They use people's home computers. So anyway, this is a summary. I'm going to skip this. There's a lot of different kinds of pulsars, and I'll skip that. But last thing, the millisecond pulsars are very important, I think, for a number of reasons. This shows you the number of millisecond pulsars in the so-called in the field. They're not in a cluster or something. And the ones in red were directly from Fermi, searching Fermi sources. And some of those pulsars, the radio telescope people realized a long time ago that you might be able to detect very low frequency gravitational waves by timing an array of pulsars spread in the galaxy, and if there was a coalescence event involving supermassive black holes somewhere or a stochastic background sweeping through the galaxy, it would introduce correlated timing variations in the pulse arrival times from pulsars in different places on the sky. Okay, long story behind that, but there has been no detection of gravitational waves yet from this. People will argue when that might happen, but we sort of early on said, oh, Fermi can't contribute to this, because from the brightest one in the sky, we get one photon every couple of minutes. So what can we do? Well, it turns out there is something we could do, and this was recognized by, among others, Matthew Kerr, who's at NRL, and Aditya Parasarathi, who's at the Max Planck Institute for Radio Astronomy. So they led some work by the collaboration on using Fermi gamma ray pulsars, just gamma rays, to set limits on a stochastic background of gravitational waves, nanohertz gravitational waves. So they selected about 35 millisecond pulsars that were gamma ray pulsars, and what they found is that the limit they were able to set is within a factor of 5 in amplitude of what the radio pulsar people have been able to do over the last 10 years. Now you might ask, well, how can we do that? Well, first of all, the periods are very long. And secondly, once we have a discovery of a pulsar found by the radio community, we get to do the timing all the way back for the entire time we've been in orbit. So that provides a lot of leverage. So anyway, that was done. And looking forward, this was published last year in Science, within, if you're an optimist, 5 years, but probably more realistically a decade, we should be able perhaps to get to the level competitive with or comparable to the radio pulsar timing. Now, why is that important? Well, if they discover something or we discover something, it's wonderful to have a different window that has somewhat different systematics. So that's something to think about for the future. So anyway, I will stop there, or almost stop. There's a lot coming up. Gravitational waves, LIGO and Virgo, LAT pulsar timing array looking very long term. I didn't have time to talk about it, but correlations with high energy neutrino telescopes, IceCube, and so forth. So all this multi-messenger astrophysics. And what has been important, I think, and I really want to end with this point, is that international collaboration has really been what made a lot of this possible. It would not have happened without it. And I gave you 2 examples in this talk, but there are many others. Now, what are the lessons you learn from doing this? It's not easy, but I think one, scientific inquiry is increasingly a global endeavor, particularly in a field like this. I think it's essential. And effective collaboration is essential, and I think can be rewarding. And so some of the things I think are needed are, one, everybody has to share in the passion for the science that you're going to do. Secondly, problems inevitably arise, and there are challenges, and those got to belong to everybody. Everybody has to own the problems, and everybody also has to own the successes. And finally, last word of advice, which I keep telling myself, but anyway, is be optimistic. Success takes a lot longer than you think. So with that, I will stop, skip that, and say thank you.
Let me just say thank you very much, Peter, for a very lucid account of a very exciting project, and it's still going on. And I would just add one thing, actually, the other thing this needs, and that is effective leadership, which leads to a happy collaboration. And this really has been a happy collaboration. And thank you, Peter, thanks for that too. Now, I've got the next question.
Roger's a member, by the way.
Yeah, I'm a member. But how long physically can Fermi go on observing?
Well, the hardware, there have been some hardware failures, but NASA is very good at mitigating those. There was a problem with solar panels, but so far, all the systems are working well. There are no expendables, and I'd say one thing NASA is looking at right now is there's a lot more satellites in the orbit altitude we're at, thanks to some, we won't say who, but anyway, among others. And we're looking at actually boosting the orbit. Now, it turns out Fermi has a propulsion system. And the reason it was put there was to have a graceful exit from orbit at end of mission life and land it somewhere in the Pacific Ocean and so forth, because of the mass of the spacecraft and everything. It turns out we haven't used it for that yet, but it turned out to be very useful for dodging errant spacecraft in orbit, such as a Soviet-era spacecraft that might have hit us. We dodged that one. We can also use it to boost the orbit, and we'll probably do that next year sometime. So.
Okay. Yeah.
Peter, is this kind of thing, do you always build a spare in case the first launch happens?
I was thinking that when we launched it, do you always build a spare? The answer is no. NASA's self-insured is what I guess, I don't know. No.
The point is that the science project takes long. If you don't have a spare, it should be pushed back by another 10 years.
I know. But I don't know when NASA, they used to build spares, and I think they spent a lot of time, and for good reason, really checking everything over and over again.
Sometimes they launch the spares, yes. Okay, question.
So I'm a little bit curious if you could elaborate on how pulsar timing is done with gamma rays.
On how what?
Pulsar timing. Because you said earlier that you can't actually see the periodicity of pulsars with gamma rays. So how can you do that without the periodicity?
You can't see, I'm not sure
Well, you can, you measure the periods. Well,
I mean, how do we discover?
Misunderstood the,
well, we do see, the first thing when we see a gamma ray pulsar, if it's Fermi, is we don't see it pulsing. We have to search for a pulse period. And what complicates that is these pulsars are losing energy because they're rotation powered. So they're spinning down. For long periods, that's not such an issue. But for very short periods, you won't stay in phase if you're folding the data in a blind search. Radio, if they're also pulsing in radio, and the beaming of the gamma rays in the radio is very different often. They don't necessarily align. But if we have, that's why this partnership with the radio community, because they can look very deep, very fast at a Fermi unidentified source and see if there's a radio pulsar there. And if there is, we have a handle on how to search in gamma rays. So it really we know the thing's emitting gamma rays, whatever the object is. We just don't know if it's actually that pulsar. Because again, our error boxes are still relatively big. Compared to egret, this could not be done with egret because the error boxes were, let's see, literally about that big on the sky. I mean, they were huge. Fermi, they're a small fraction of that. So a radio telescope, like, you know, the ones I showed you, with one pointing, more or less, at our error box where our source is, they can do a deep dive and see if there's a radio pulsar. With egret, you would have had to search around and around, and there just wasn't a lot of time devoted to that.
Phil, thank you, Peter. That was really wonderful talk. I was going to ask, what's the singles rate? Just because
what's the
singles rate? How many gamma rays per minute? But
oh,
I'm going to ask something else. Can you explain that picture behind?
Oh, that. I just, yeah, sure. That's, you see the date there?
Yes, that's fine.
This was early on. We have to do an update on this, actually. Well, first of all, we cover that entire celestial sphere more or less uniformly every 90 minutes by rocking the orbit up in a few degrees, I don't know, 10, 20 degrees off the zenith one way and then the other way. So we get the poles of the orbit and everything. And then this map that's then projected onto the sphere, and the cadence here is, well, you can see some of the sources varying. There's a certain amount of shot. The gamma ray rate in Fermi is about, somebody will correct me, I think it's about 3 per second.
3 hertz, yeah.
Yeah, it's about 3 hertz for everything we're looking at. The Vela pulsar is about 1 every 2 minutes.
Right, so what I'm seeing there can't possibly be that.
Can it possibly be what?
The result of 3 per second, right?
No, you're seeing the frame rate. The frame rate is one day at a time.
Okay, so everything we're seeing there is that actually what was observed at the date that's flashing at the time.
Wait a minute, sorry.
Right?
Yeah, we get a third of a million. Yeah.
Yeah. Anyway, okay, I was going to end with that. That's my favorite painting. Anyway.
More questions?
Why?
Very early on, lab detecting high energy photons from gamma ray bursts, there was excitement and collaboration. Had a paper on the Lorentz invariant violation.
Oh, that was
What's happened to that?
that was a paper published in Nature. Back there was, I think Vai's referring to one of the early gamma ray bursts we saw. That was at a fairly high redshift. I forgot what it was, and we compared the other instrument which works at low energies. The glass burst monitor goes down to 6 kilovolts, and we looked at the pulse profile, and it turns out you could set limits on violations of. You could set limits on how the speed of light might vary with energy. I frankly didn't, depending on who I showed it to at Stanford, they either laugh or say, oh, that's great. But it set an interesting limit, so it was constraining in that sense. And that was 2010, I think?
Yeah, very early.
Yeah, it was fairly early, yeah. But I happen to believe, well, anyway, it was actually an interesting limit to some people.
So, we're getting on. This
Yeah.
has been a wonderful talk, Peter. Thank you very much indeed.
All right.
And let me. There you go. Yeah. Very good.
I was going to start with that.
Yeah.
And then I realized
That's good.
He painted that when he was in an asylum.
Yeah, that's right. Yes.